Okay, so in this lecture, we will be actually introducing the concept of adjoint operators on a inner product space. Before that, we will cover a slightly important topic on orthogonal complements. I won't say it to be a topic, I'll rather say it's a theorem on orthogonal complements. And then we will be moving into the concept of adjoint operators. After we do the concept of adjoint operators, we will be covering the topic least square approximations, where we will see a slight application of the concept of best approximation, which we did in the previous lecture. So, if you recall what orthogonal complement was, so let a minute. Yeah, I guess this will do. Okay, so let V be an inner product space and let W be any subspace of V. Okay, then uh, the orthogonal complement of W is basically the connection of elements which we write as like this, let's say, in V, such that the inner product of W, W, I don't know exactly what the symbol is called, with W is 0 for all W in capital W. Okay. So what we are actually doing here is that we are collecting all the vectors which are orthogonal to the elements in W. And this collection is said to be the complement of W. Okay. I guess this is called a perp. Okay, W perp, I guess. Okay, that's not a matter of concern at all. The definition which we are going to speak about is quite important. Or sorry, the theorem which we are going to speak about is quite important. In a way, this theorem actually helps us decompose any given inner product space into a direct sum of any arbitrary subspace of it and the orthogonal complement of that subspace. Okay. The theorem is as follows. Let S be a certain collection, say V1, V2 till Vk, be an orthonormal set. Now, quick recall that orthonormal sets are already linearly independent. Be an orthonormal set, and so we will be talking about basis, right, in this theorem. So we need a finite dimensional inner product space. So in a, let's say, n dimensional inner product space, okay, then first thing first, which is quite relatable as well if you have done a basic course in linear algebra, which says that, like, we know that any linearly independent subset can be extended to form a basis, right? So that is exactly what we are doing here. We say that we can extend S to an orthonormal basis of V. Okay, so S can be extended. S can be extended to an orthonormal basis of V. Okay. Number two, that if I choose W to be the span of S, okay, let me do a bit more here. Let me fix some symbols in the theorem itself. So I want to say that S can be extended to an orthonormal basis of V. And let me precisely give the basis as V1, V2 till Vk. That is, we are precisely keeping the vectors of S. And we have some extra vectors which we denote as Vk plus 1 till Vn, because we will obviously have n vectors since we are talking about a basis of n dimensional vector space. Okay. Number two, we say that if W is the span of S, then if I consider the collection S1 as the vectors in the basis, in the orthonormal basis, other than the vectors which are already present in S. Okay, that is, S1 is the collection of elements Vk plus 1 to n. Vk plus 1 to n. then this will be a basis for the orthogonal complement of W. Then S1 is a basis for the orthogonal complement of W. And number 3 is that if W is a subspace of V, then the dimension of V is equals to dimension of W plus the dimension of the orthogonal complement of W. Okay. Now to prove this, what we exactly need is the standard replacement theorem. If you recall what the replacement theorem was, it was exactly the statement that any linearly independent collection in a finite dimensional vector space can be extended to form a basis if it has less number of elements than V. We can actually prove a stronger statement. Actually, the replacement theorem is not exactly this what I said. The statement which I said is actually a corollary of the replacement theorem. So what we exactly do is that we first prove the replacement theorem for a completion, and then we state the completion of basis, the extension of basis in terms of as a corollary to the replacement theorem, and then we will be proceeding with the proof, because once we have the replacement theorem in hand, then the proof is pretty trivial, right? Because if I just say, what I can do is that if I can extend S to a basis, I'll do that, and then I'll use the Gram-Schmidt orthogonalization process to orthogonalize the vectors in the basis I have to form an orthogonal basis. Since the vectors v1 till vk, they are already orthogonal, so even after the Gram-Schmidt orthogonalization, v1 till vk are still in the orthogonal basis which we achieve. The rest of the vectors which we achieve by the Gram-Schmidt orthogonalization process, we can just normalize them, or I should say, I should not say that. The other vectors other than these vk vectors, which I achieve, they are again, they just form an orthogonal basis for S, and then we just need to normalize them. Okay, so v1 till vk are already there. The extra vectors vk plus 1 till vn which we get, it readily comes from the Gram-Schmidt orthogonalization process, and then we just need to normalize the vectors. There's nothing too complicated there. Okay. Moreover, if I talk about the second theorem, we already know that v1, I mean this collection I have got here is orthogonal. So if I consider the elements in S1, then each of these vectors will be orthogonal to the vectors v1 till vk. So obviously S1 must be contained in the orthogonal complement of W. But then if I consider an arbitrary element from W, I mean from the orthogonal complement of W, and represent it as a linear combination of this orthogonal basis, then again by orthogonality of the vectors, we will get a linear combination of the vectors vk plus 1 till va. And the third statement, it readily comes from statement 1 and 2 as well. Okay. So first what we do is that first we prove the replacement theorem. The replacement theorem. Okay. Let me just decrease the width a bit. I guess this will do. And let me change this a bit as well. Yeah, I guess this will do. Correct. Okay. So what is the replacement theorem? Let V be a vector space generated by a set G consisting of n vectors. And let L be a linearly independent subset of V, consisting of m vectors. Okay, consisting of m vectors. Then m must be exactly less than equals to n. M must be less than equals to n, and there exists a subset of G consisting of n minus m vectors such that L union H generates V or spans V, whatever. Clear? So this is the replacement theorem. So let's give a proof of this. What we do is that we induct on M. Okay, we induct on M. So let me precisely write it first. We induct on M. Okay, let me change this color a bit. That's too dark. Yeah, this will do. Okay, so we induct on M. So what is the base case then? If M is equals to 0, let's say. Okay, for M to be 0, L is empty, right? So if L is empty, then the statement is vacuously true for H to be G, right? Because we already have by our given hypothesis in the theorem that G generates V. Then H equal to G does the job, right? H equals to D, G does the job, right? So therefore, we assume that the statement is true for some m greater than 0, and we prove it for m plus 1, right? These are trivial statements. We prove it for m plus 1. Okay, so to do this, what we actually need is that we consider this linearly independent subset of V to be a collection of m plus 1 vectors. Okay, let L be a collection of m plus 1 vectors. So we have v1 v2 till, let's say, vm plus 1. Okay, so let this be a linearly independent subset of V, right? Now we know that a subset of a linearly independent subset is still linearly independent, right? Since L is linearly independent, therefore the collection v1 v2 till vm is again a linearly independent subset of V. Now if this is a linearly independent subset of V, so we have m collections, and we have assumed that this statement is true for some m greater than 0. Therefore by induction hypothesis we can say, therefore by induction hypothesis, m must be less than equals to n, right? M must be less than equals to n. This simply follows from the induction hypothesis. I guess you can easily observe that. Moreover, what more do we get from the induction hypothesis is that we have a collection, and we have a set, say u1, u2. So we have n minus m vectors from G, such that the union of these elements, and these elements will generate V, right? Such that the collection v1 till vm union the collection u1 till un minus 1 n minus m, this will generate V, right? So in other words, so if it generates V and v m plus 1 is a vector from V, right? This implies there exists scalars, obviously not all 0, we will examine on that, say a1 till am, and let's say b1 till bn minus m, such that if I take a linear combination of these vectors we have, so a1 v1 plus a2 v2 and so on till am vm plus b1 u1 and so on till bn minus m un minus m, then I get vm plus 1. This solely follows from the fact that the union of these sets generates V, and vm plus 1 is a vector from V, right? Okay, now observe that now n minus m cannot be 0, right? So n minus m should always be greater than 0, as if not, then observe that vm plus 1 is a non-trivial linear combination of the vectors of the vectors v1 till vm. But this contradicts the fact that the collection v1 till vm plus 1 was linearly independent, right? In a linearly independent set, you cannot express any of the vectors as a linear combination of the other vectors. So which contradicts the fact that L is linearly independent, where L was the collection of vectors v1 till vm plus 1, right? L is linearly independent. Therefore, n must be greater than m, and since we are talking about integers, this precisely means n must be greater than equal to m plus 1, right? Okay. So one part of our hypothesis is clear. Moreover, some bi must be non-zero, because if all the bi's are 0, then again we reach the same contradiction, that if all bi's are 0, then vm plus 1 is a non-trivial linear combination of the vectors v1 till vm, and hence it contradicts the linearly independence of L. So moreover, some bi is 0, say b1. So we can think of it as some sort of a reindexing, where if I get some scalar to be bi to be 0, then I reindex that collection to be to say that b1 is 0. Say b1 is b1 is non-zero. Okay, so we have b1 is non-zero. But if b1 is non-zero, then I can write u1 as a linear combination of all the other vectors present in this equation, right? Then u1 can be written as b1 inverse of minus a1 times v1, so on and so forth, till b1 inverse of minus am vm plus b1 inverse of vm plus 1, and then we again do the same for the vectors u2 till un minus 1 n minus m, because u1 is already there. So plus b1 inverse of minus b2 of u2, and so on and so forth till b1 inverse of minus bn minus m un minus m, right? Un minus m, right? Clear? Now let H be the set u1 till u2 till un minus m. Okay. Clearly, so we have expressed u1 as a linear combination of the vectors v1 till vm plus 1. Therefore, the vectors from L and the vectors u2 till un minus m, which are the vectors from H, then clearly u1 is inside the span of L union H, right? Clear? Okay. So this is one obvious observation, say one. Moreover, see clearly the way L and H has been chosen, each of these vectors v1 till vm, u2 till un minus m are all in the span of L union H, because the vectors v1 till vm are themselves in L, the vectors u2 till un minus m are themselves in H, so individually they are themselves in the span of L union L, the span of L union H as well. That's a trivial observation. So we have u1 in the span of L union H, v1 till vm, and u2 till un minus 1 n minus m in the span of L union H. So this implies that v1 till vm and u1 u2 till un minus m, all of these vectors are in the span of L union H, right? But now observe the fact that these vectors v1 till vm and u1 till un minus m, by assumption, it spans V, right? It generates V. This comes from the induction hypothesis, because we had said that for any m greater than 0, if I have a linearly independent subset comprising of m elements, then m must be less than equals to n, and I will get a n minus m vectors from G, and the union of which will span V. So since these vectors span V, therefore V must be in the span of L union H. But observe the fact that L is a subset of V. H is also a subset of V because G generates V. In a way, G is automatically a subset of V. H is a subset of G. So therefore, V must be equal to the span of L union H. You can easily justify this fact because L if is in V, H is in V, L union H will also be in V. I mean the so if you take the span of these elements, then by closure the span is also in V. So the other way around it's quite trivial, right? So V is equals to the span of L union H, right? Clear? Okay. And that was exactly what we wanted to prove. Moreover, observe one thing which we have not proved yet is the inequality of L and N and M. That what are the number of elements in H? So observe that H contains the elements U2 till UN minus M, right? U2 till M minus M, which implies the number of elements in H is N minus M minus 1, right? Because U1 is not there. So it's N minus M plus 1, and that's exactly what we wanted to prove. So therefore it follows from induction. Therefore follows from induction. Follows from induction. Okay. And a corollary of this proves, if I talk about the corollary of this replacement theorem says that every linearly independent subset of V of dimension n, where V is a vector space of dimension n, can be extended to a basis. Can be extended to a basis. Okay. How do we prove this? So let L contained in V be linearly independent, and let's say the number of elements in L is M. Okay. Then we follow from replacement theorem. Then by the replacement theorem, there exists a set H in the basis of V, right? Because I can replace G in the replacement theorem by a basis of V, right? Because when we had stated the replacement theorem, there nowhere we discussed about the finite dimensionality of V, right? So therefore we had chosen G to be an arbitrary generating set. In this case, we are talking about a finite dimensional vector space V. Hence, we can talk about the generating set being a basis. Hence, we are considering H out of the basis of V. And what are the number of elements which H will constitute? It will constitute n minus m elements, with n minus m elements such that L union H span V, right? But then observe that L has m elements, H has n minus m elements. So if there is no repetition of elements in L and H, that is every element in L and every element in H are mutually distinct, then the number of elements in L union H is n, right? If not, then the number of elements in L union H must be less than n. So observe L union H has at most n elements. But we know that in a finite dimensional vector space, a finite generating set contains at least n vectors when the dimension of the vector space is V. But since dimension of V is n, any finite generating set has at least n vectors. So L union H is a finite generating set which has at most n elements. But since it's a finite generating set of a finite dimensional vector space, it has at least n vectors. This implies L union H has exactly n vectors, but V has dimension n, and L union H is a collection of n elements which generates V. So this clearly implies that L union H is a basis of V. Is a basis, right? Okay. So this was, one of the most important proofs when you study a basic course in linear algebra, where we study the concepts of basis. Okay. Now let's come back to the proof. Okay. So in the proof, as I said, that I already have an orthonormal set proof S, which was given to be the collection of elements V1 till Vk, is orthogonal. Orthogonal, or it was orthonormal. I guess it was orthonormal. Is orthonormal, hence linearly independent subset of V. Therefore, S can be extended to an ordered basis, say S dash, which is given by V1 till Vk, and we have Wk plus 1 till Wn for V. I guess in the theorem itself we have stated V to be of dimension n for V. Then what we can do is that by Gram-Schmidt orthogonalization process, what we have is that S dash can be used to generate an orthogonal basis for V, which still preserves the vectors V1 till Vk, because they are already orthogonal. So the orthogonalization process which will cause no effect to them. The orthogonalization process will specifically change the vectors Wk plus 1 to Wn with mutually orthogonal vectors, say some uk plus 1 till Un, and we will get an orthogonal basis which still consists of the first k vectors to be V1 till Vk. Okay. Normalizing. Now V1 till Vk are already orthonormal. So normalizing the other vectors will give an orthonormal basis, right? Which, as given in the theorem, can be assumed to be V1 till Vk and then Vk plus 1 till Vn, right? Okay. That is the n minus k vectors. We are talking about the rest of the n minus k vectors other than V1 till Vk. We just orthonormalize them and we have our answer. Okay. So this was, I guess, the statement 1, right? Statement A or 1, I don't remember exactly. Okay. Number 2 is also pretty observable, which I was discussing before I started this proof, that if I consider S1 to be the elements Vk plus 1 till Vn, then since the collection V1 till Vk, Vk plus 1 till Vn is orthogonal, you can just speak of orthogonality. Therefore, every vector V1 till Vk, therefore Vi Vj, let's say Vi Vj is 0 for all I is equals to 1 to k and j is equals to k plus 1 till n. But that readily means that every vector in S1 is orthogonal to every vector V1 till Vk. S constitutes the vectors V1 till Vk. This implies S1 must be in the it should be in the in the orthogonal complement of S. What more can we say? What was the theorem? I forgot. What was the statement in the theorem? Okay, we had assumed S to be the okay. Let me get back to what I wanted to say. Correct. Okay. Now W is equals to the span of S. So if these vectors, the vectors in S1 are orthogonal to each vector of S, then obviously the vectors in S1 will be orthogonal to every linear combination of the vectors in S. and hence it will be orthogonal to every vector in W. So there must be an element. So each of the vectors in S1 are elements from the orthogonal complement of W. In other words, S1 itself is in the orthogonal complement of W, right? Okay. So if S1 is in the orthogonal complement of W, and then what we primarily have is that any linear combination of the vectors in S1 will also be in the orthogonal complement of W, because W, it follows from closure. So what we need to show is that W perp is contained in the span of S1. That's what we exactly need to show, right? How can we show that? Let X be in B. Then, if you recall, for an orthogonal basis or an orthonormal basis, we can primarily talk about an orthogonal basis. So if we have orthogonal basis, then X can be represented as a linear combination in this form. So the orthogonal basis was the elements V1 till Vn. So I is equals to 1 to n. X, the inner product of X with Vi times Vi. Right? This we had covered in the lectures in which we had introduced the concept of orthogonality, if you recall. Therefore, if X is in W perp, then the inner product of X with Vj becomes 0 for all j is equals to 1 to k, right? Therefore, this linear combination gets shortened to I is equals to k plus 1 to n, inner product of X with Vi into Vi, but this is in the span of S1, right? So this implies W perp is in the span of S1, which implies W perp is equals to the span of S1. I guess this part is clear. Okay. So the last thing which we now require to prove is the fact that dimension, the case of dimensions. So how do we do that? See, we have already shown the fact that if I consider orthonormal, let's say an orthonormal set consisting of k elements from a finite dimensional subspace V, then it can be extended to form a basis for V, right? So C can be followed like this. So dimension of V is n, but n can be written as k plus n minus k. So k is the dimension of S as given, and n minus k is clearly the dimension of S1 as given, right? Is it clear? Is it clear? Okay. Now, the thing is basically what I said the word that the span of S1 is contained in W perp by closure. It's basically because of the fact that the orthogonal complements, they all also form subsets. I mean subspaces. They also form subspace. Okay. Yeah. Okay. The proof was quite a bit rigorous, but it was easy at the same time. Okay. So now we come to what I actually intended to introduce, but it's already 30 minutes after I am introducing it. Adjoints of a linear operator. Okay, adjoints of a linear operator. Okay. After this lecture, whatever we are going to study, it will be highly dependent on the concept of adjoint operators. Okay. What we try to do is that our primary goal is to establish the fact that if I talk about a certain linear functional for a given inner product space, then provided a unique vector y in V, there exists a linear functional which can be expressed in terms of that vector. Okay, so in a way I am trying to establish a correspondence between linear functionals and vectors in the vector space we will be talking about, or in the inner product space specifically we will be talking about. Okay, let V be an inner product space over some field F. Now we know that F is either real or complex by definition of an inner product space, so that I am not mentioning anymore. Let Y be a vector from V. Then let G be a linear functional, or let G be a function from V to F, such that g of x is the inner product of x with y, then it is easily observable that g is linear. Because if you consider g of say cx1 plus x2, where c comes from f, x1 and x2 comes from v, then it is the inner product of cx1 plus x2y. Then you can break it down as c times x1y, inner product of x1y plus inner product of x2y. So it is c times g of x1 plus g of x2. So indeed it's linear. Now our goal is to say that if I choose an element, a vector y from V, then I can also give a linear functional in terms of y. Okay. So let me state it as a theorem. Let V be a finite dimensional inner product space. It being a finite dimensional inner product space is important because the introduction will be given in terms of a basis, primarily an orthonormal basis. Let V be a finite dimensional inner product space over F, and let G from V to F be a linear transformation. Then there exists a unique vector y with respect to which G can be defined, such that G of x can be defined as the inner product of x with y, and this can be done for all x in V. Okay, so let's prove this out. Proof. First thing first, we see that we are given V to be a finite dimensional vector space. The reason for that is we will assume an orthonormal basis, which we know surely exists because we have already showed that every finite dimensional vector space has an orthogonal basis. Hence, normalizing the vectors will give you an orthonormal basis. That's quite trivial. So the proof comes from the fact that let V V1 till Vn be an orthonormal basis for V, and let y be given as sum over I is equals to 1 to n g of vi bar multiplied with vi. Okay. Surely g of vi bar is a scalar quantity. Hence this multiplication is well defined because V is after all a vector space. Right? Now what we do is that we consider the transformation, linear transformation. Let h be a linear of V to F, a linear functional, such that h of x is given as the inner product of x with y. We have to show that h equals g. But observe that since beta is a basis for V, so if I establish an equality of h and g with the vectors in the basis, then it is sufficient to establish the fact that h must equal to g for every vector in V, because every vector in V will be a linear combination of the elements in basis, and h and g both are linear, right? Then what is, so my question is, what is h of Vj for 1 less than equals to j less than equals to n? So h of Vj by definition is the inner product of Vj with y. So hence it's the inner product of Vj with a summation over I is equals to 1 to n g of Vi times Vi, and g of Vi has a bar. But these are, so it can be distributed in terms of summation, and all these scalars they will come out after taking their conjugates. The conjugate of g of Vi will, the conjugate of g of Vi bar will be g of Vi. So it will come out to be as I is equals to 1 to n g of Vi bar. Sorry, no bar will be there because we are bringing it out of the inner product. Right? This follows from the axioms or the properties of inner product. And here we have Vj with Vi. But we know we are talking about an orthonormal basis. So Vj Vi, so this quantity will correspond to delta Ji. It will equal 1 if j is equals to I, and it will equal 0 if j is not equal to I. Hence you get only the term g of Vj, and this happened for any arbitrary vector Vj where j ranges from 1 to n. This implies H equals to G on beta, and since beta is a basis of V, this implies H is equals to G on V. That was exactly what we wanted to prove, right? Okay, this follows from linearity and the fact that beta is a basis of V. Now suppose this Y is not unique. Suppose G could also be written as XY dash, and this happens for all X in V. That's quite an important statement. But G can also be written as XY, right? So this implies the inner product of XY dash minus the inner product of XY. This must equal 0. But that implies the inner product of X with Y dash minus Y must equal 0. But this happens for all X in V. So if I consider X to be a non-zero element, for the inner product to be 0, Y dash minus Y needs to be 0. But that means Y dash must be equals to Y, right? Therefore, this vector we have chosen Y is indeed unique, right? This brings us to the introduction of what the adjoint of a linear operator is. The importance of introducing the concept of adjoint is the fact that provided a matrix, we know what the concept of a transjugate of that matrix is, right? I'm trying to say is that given a square matrix, let's say, given a square matrix A, we know what is A star, which is the transjugate of A. If you recall, what is the transjugate of A? So A star is basically the transpose of A and taking the conjugate of each individual element, or you can do it also vice versa. You first take the conjugate of A. Conjugate of A means taking the conjugate of each individual element in A, then taking its transpose. They are primarily the same. My question is that if I start with a matrix and I can well define its conjugate, then I must be able to associate a linear transformation. Obviously, now we know that over finite dimensional vector spaces, linear transformations are in some sort of a 1-1 correspondence with square matrices. So therefore, provided we start up with a simple square matrix, I can associate a linear operator to that matrix. And I can define a conjugate to that matrix as well. So I must be able to associate a linear operator to that conjugate of the matrix. This linear operator is what actually is the adjoint of the linear operator corresponding to this matrix we started with. Okay. So we introduce the concept of the adjoint of a linear operator in terms of a theorem, which says that let V be a finite dimensional inner product space and let T be a linear operator on V. Then there exists a unique function T star from V to V such that the inner product of Tx with Y is same as the inner product of X with T star Y for all xy in V. Moreover, T star is linear. Okay, that's what we exactly need to prove. Okay, so the proof is quite simple provided the previous theorem is there. See, let Y be in V. Okay, then we can define the linear functional gx x2 yeah, we can define it to be gx to be the linear transformation, say txy. Yeah, we can do this txy. This happens for all x in V. Clear? Okay. Now this is again linear. G is linear provided the fact T is linear and provided the fact which we had previously established. When we had defined gx to be linear product of x with y, it came out to be linear. On same terms, we can also prove this to be linear provided T is linear, right? So there is nothing too complicated here. I'm not giving the proof. You can do it on your own. Why? Okay. Now consider y prime to be an arbitrary element of V. Now we had previously seen obviously in the previous theorem that provided a linear functional is there, we can choose a vector, a unique vector from V such that the linear functional can be written as an inner product of the vector x with this unique vector y, in this case y prime. Then g of x can be defined as the inner product of x with y prime, right? Since g is a linear functional defined on V. Let T star be the linear operator such that T star maps y to y prime. Okay, clear? So now observe the fact. Therefore, now gx is defined as the inner product of xy prime and gx was defined as the inner product of txy. Therefore, gx is defined as the inner product of txy, but we have also defined it to be the inner product of xy prime, and we choose y prime to be the image of y under t star, right? By uniqueness of y prime, which we have proved in the previous theorem, this is sort of a well-defined statement, and it clearly holds, right? Okay. So the existence of this T star is quite well defined. Moreover, we need to show that this T star is linear. How can we show that? To show T star is linear. To show this, what we do is that let C1 or let C be an element of F. F is the field over which V is a finite dimensional linear product space, and let Y1 and Y2 come from V. Okay. Then what is the inner product of X of T star of C times Y1 plus Y2? Then by definition of the linear operator, how we constructed T star, it is same as T of X with CY1 plus Y2, right? Okay. But then it can be distributed as C bar times inner product of Tx with Y1 plus the inner product of Tx with Y2. But then this can be done as C bar of the inner product of X with T star Y1 plus the inner product of X with T star Y2, the way we had constructed T star. But then it can be written as X times X, the inner product of X with C times T star Y1 plus the inner product of X with T star Y2, and then if I just add them back, I get X, the inner product of X with C times T star Y1 plus T star Y2, and this happens for all X in V, right? For all X in V, and Y1 and Y2 was chosen arbitrarily. So this implies if I bring this on the left hand side, or I do not even need to bring this on the left hand side, we have an equality in terms of X, so we must also have an equality in terms of the second element in the inner product. Or you can also bring it to the left hand side, then enclose the inner product to exactly get the fact that the inner product of X of T star CY1 plus Y2 minus C times T star Y1 plus T star Y2 is 0, and this happens for all X in V. So this implies T star of CY1 plus Y2 must be exactly equal to C times T star Y1 plus T star Y2, which implies T star is indeed a linear operator on V. Right? Right? Okay. Is T star uniquely determined? Okay. So what we have already proven is the existence of T star, the linearity of T star. Is T star unique? Okay. Then it also follows from the same statements of arguments that let U be a linear operator on V such that we can define Txy to be Xuy. But we know that Txy can also be defined as X T star Y, and all these statements happen for all X in V. but then again we have x time inner product of x with t star minus u of y to be 0. This happens for all x in V and for all y in V. So I should mention it as well for all y in V. But that implies that the second element must be equal to 0 for all y in V, but that will only happen if t star minus u is equals to 0 or t star is equals to y. So hence we have established a linear operator which is linear, which obeys the case that the linear operator for if you start with the linear operator t, then tx inner product of tx with y is same as the inner product of x with t star y, and also it is uniquely determined. Okay. For a linear operator t on V, t star is said to be its adjoint. Okay. Now the question which should obviously arise is that the proof of this existence of T star, it was primarily dependent on the fact which we proved in the first theorem of this lecture after the rigorous proof of the orthogonal complex. I mean this theorem. I do not give numbers to the theorems, and hence I get often confused. Yeah, I'm talking about this theorem. Okay, this theorem was indeed used to give the existence of T star, and this theorem as well dependent on the existence of a orthonormal basis, of a finite orthonormal basis. Hence the case for the inner product space to be finite dimensional is required for an elegant existence of T star, right. Therefore, for the existence of for to ensure the existence of T star, V being finite dimensional is enough. That what I mean to say is that if we start with a finite inner product, a finite dimensional inner product space, then for every linear operator defined on an inner product space, we will always get an adjoint operator to it. But we cannot ensure this for an infinite dimensional inner product space for obvious reasons, because we started all these construction using a finite orthonormal basis, right? We cannot ensure the existence of the adjoint operator for an infinite dimensional inner product space. But surely they might exist. If they exist, but if there exists an adjoint operator T star for a linear operator T, then we simply define it as, then we can define it to be the operator such that Tx of y must be equals to x T star y for all vectors x and y in V, right? So if it exists, then it surely should obey this condition, and that's where that's where the definition comes for infinite dimensional inner product spaces. Okay, I guess this part is clear. Now the last claims I'll be doing in this lecture, because it's already almost a 1 hour long lecture, is that how we started thinking about this adjoint operator. As I said, that we started intuitively guessing about its existence from the fact that given a square matrix, we can talk about its conjugate. So we should establish the fact that the matrix associated with the adjoint operator is indeed the concept of a conjugate for the matrix of the linear operator we will be starting with. So theorem: let V be a finite dimensional inner product space, and let beta be an orthonormal basis for V. If T is a linear operator on V, then the matrix of T star with respect to beta is same as the conjugate of the matrix of T with respect to beta, where for a matrix A star denotes its conjugate. A star denotes its conjugate. Now, how does this follow? Firstly, observe the following fact, which we had already established in the previous lectures where we talked about orthogonality or orthogonal basis, and it sort of was useful in this lecture as well. That if I start with an orthogonal or specifically you might say an orthonormal basis as well, an orthonormal basis, an orthonormal basis for V, then then primarily we are talking about orthonormal basis, so let's stick to a concept of orthonormal basis. Then for all x in V, we can write x as sum over I is equals to 1 to n inner product of x with these vi's, where vi's constitute the orthogonal basis. Okay, with vi, where vi's are the vectors from the orthogonal basis, orthonormal basis. But then since T is a linear operator, so Tx is also a vector from V. So Tx can be written as summation over I is equals to 1 to n inner product of Tx Vi with Vi. But then what is the T of Vj, where j is again a vector from the orthonormal basis itself? Then it is summation over I is equals to 1 to n inner product of T of Vj with Vi multiplied with Vi. But then this is sort of a matrix representation. If you carefully observe, we can choose this to be the matrix Aij. Okay, we will necessarily require this to complete this proof. So suppose I start with this representation itself, where I can write Bij to be the inner product of T star Vj with Vi. Okay, this readily comes from the matrix of T star with respect to beta. Okay, this A is assumed to be the matrix of T with respect to beta. This A is nothing but the matrix of T with respect to beta. The beta is an orthonormal basis. Bij is equals to the inner product of T star Vj with Vi, but I can write this as the inner product of Vi with T star Vj bar. But this is obviously equal to the inner product of bar of the inner product of Tvi Vj, but then this is nothing but Aj bar, but observe Aj bar is the bar of the transpose of A. So I am taking the ijth element of this, and it is exactly the ijth element of the conjugate of A. So this means B must be equals to A star, right? Is this part clear? Okay. Now, since we have established this fact for linear operators, we can also start with a matrix. And then establish the same fact for the linear operator corresponding to these matrices, right? Like if you recall, now I often get confused while saying orthonormality and orthogonality. What I try to say, I mean, from where did I come up with this concept? Is recall when we were studying orthogonality, we had said that if I consider an orthogonal basis, say the basis, I'm just recalling this fact. If I consider B to be the orthogonal basis alpha 1 to alpha n, then any vector any vector alpha can be represented as summation over alpha with, I guess, summation alpha with alpha k upon norm of alpha k times alpha k, right? This was something which we had previously talked about, right? But then observe that if I talk about an orthonormal basis, then this norm becomes 1, right? Then this norm becomes 1. So if this norm becomes 1, then it exactly gives the statement which we talked about throughout this lecture, right? Right. I hope you are getting what I'm trying to say. Clear? Okay. Achha, 1 second. 1 second. Yeah, I need to talk about one more theorem. Um, yeah, I guess, yeah, okay, let's talk about one more theorem. Okay, I guess there will be a square as well here. Yeah, sorry, there will be a square as well. Sorry. Okay, so I'll talk about a corollary rather. I'll talk about a corollary rather. Corollary, white color. Corollary. The corollary is as simple as it seems to be. So what I try to say is that if I start with a matrix, I can talk the same thing about the linear operators induced by those matrices. So let A be an n cross n matrix. Then the adjoint of the I mean the linear operator induced by the adjoint of the matrix A will be same as the adjoint of the linear operator induced by the matrix A. Okay, how can we do that? So for this, we just assume the standard ordered basis of Fn. Okay, let beta be the standard ordered basis for Fn. We know that the standard ordered basis is orthonormal in nature. But let A, by definition, is obviously the matrix of the linear operator induced by A with respect to this basis beta. Okay. Then the adjoint, the matrix of the adjoint of LA with respect to beta is the adjoint of the matrix of LA with respect to beta. This comes from the previous theorem, but then this is exactly equals to A star, but A star is the matrix of the linear operator induced by A star in terms of beta. That's where the proof ends, right? This implies the, yeah, I guess I'm true to what I'm saying. Yeah, correct. Yeah, so the matrix of them are equal, right? The matrix of LA star with respect to beta is same as LA star with respect to beta. Hence, we know that therefore LA, I mean the adjoint of LA is same as LA star, right? Because if you recall, how was this matrix defined? I mean, this operator defined. LA is defined to be AX, nothing else. Okay, so this readily follows from here as well. Okay, yeah. So we have discussed enough in this lecture. I hope you got to learn something from this lecture. In the next lecture, we will talk more about adjoints, and specifically we will be talking about the concept of the least square approximation. Okay, that will be the topic for the next lecture. So meet you guys in the next lecture.